Hello, my name is Marcial Maximiliano Chau Lopez, and this is the practice number 1 of the digital design course. The objective of this practice is to learn the basic principles of the VHDL language to simulate combinational circuits in a FPGA board. The operation of each code will be explained based on the truth table obtained from each circuit, and the result will be shown on a FPGA board. So the first circuit to be analyzed is this one, when we can observe that it is conformed by an AND gate, NOT gate, and OR gates. Well, based in this circuit, to turn on the LED, we need to obtain a number one logic over here. And to obtain a one from an AND gate, we need to get an one here and one here. And to obtain a one from a NOT gate, we need to obtain a zero here and a zero over here. With the OR gate, for the unit for to obtain a zero here, it's that in our inputs, we put a 0, 0, and 0, and 0 over here. Sorry, we need a 0. So basically, the combination to obtain the 1 and turn on the LED here is this one, which is corresponds to the first combination in the truth table. The next combinations basically don't turn on the LED because we are going to obtain a 0 in the output. So this will be the unique combination to obtain a 1 and turn on the LED. And now we are going to see the code. For the exercise number 1, this will be the code. And these ones are libraries directives that import the IEEE library and all its functions. And this section defines the practice 1 entity and have 5 ports that are 4 inputs and 1 output. And the next section defines the circuit architecture of the practice 1. And I assigned 4 signals, four internal signals as AUX, AUX2, AUX3, and AUX4 that are defined and will be used to perform logic operations. And in this part, the AUX and AUX2 perform an OR operations between pairs of inputs, which are A or B, C or D, and store the results in the corresponding signals. AUX3 and AUX4 negate the values of X, AUX, and AUX2, respectively. And finally, the output signal F is determined by performing an AND operation between AUX3 and AUX4. So now we are going to see the operation of this code in the FPGA world. As we can see in the following video, the only way for the LED to turn on is when the value of the input is a logical 0. And at the moment that we obtain a logic 1, the LED will proceed to turn off, which corresponds to the values obtained in the truth table. The second circuit is this one. We can observe that we have an AND, NOT, and OR gates, and we're going to proceed that to turn on the lid, we need to obtain a 1, and the only combination to obtain a 1 from an AND gate is that we have a 1 here and 1 here. Now, we need to obtain a 1 from a NOT, so we need a 0. And to obtain a 0 from an OR gate, we need a 0 in the input and a 0 in the other input. Now, to obtain a 1 from an OR gate, we have 3 combinations. The first one is that we have a 1 here and a 0 here. Or we can get a 0 here and a 1 here. And finally, 1 here and 1 here. Now, we can see that all of these are the possible combinations to obtain a 1 and turn on the lid, which corresponds to these lines. This one, and finally this one. There are just 3 possibilities to obtain a 1 and turn on the lid. Now, we're going to explain the code for this exercise. So we are using basically the same structure as the first exercise, and we had 4 ports that are inputs and 1 port that is an output. In the architecture, we need only just 3 signal auxiliary variables that I define as AUX, AUX2, and AUX3. And in this case, we're performing an OR operation between A and B, and C and D. And the AUX3 is to obtain a NOT operation of the AUX2 signal. And finally, the output will be the operation between AUX3 and AUX for an AND. Now we're going to see the functionality of this code in the FPGA board. So, recalling the possible combinations obtained from the truth table, we will observe that the LED will light up only 3 times. When we have an input 0, 1, 0, 0, the following 1, 0, 0, 0, and finally 1, 1, 0, and 0. This is the third circuit, and here we can observe that to turn on the LED, we need to obtain a 1, and to obtain a 1 from a NOT gate, we need to obtain a 0. This is an OR gate, and the only form to obtain a 0 from an OR gate is to get a 0 here and a 0 here in the input. And first one, to obtain a 0 from an AND gate, we have these 3 possibilities. That is that in the first input, we put a 0, and the B input to obtain a 0. The next combination is to obtain a 0 and a 1, and finally a 1 and a 0. And in the other hand, we get an AND gate, and basically it's the same combination possibilities to obtain a 0 over here. So the first one will be 0 and 0, 1 and 0, and 0 and 1. So these ones are the combinations to obtain a 1 here in this LED that turns this and corresponds to the next 5 possible combinations. And now we're going to see the code and explain its functionality. So here the only thing that we change is that we just have 3 ports as inputs, which will be A, B, and C. The F will be our output. And here we are using 3 signal auxiliaries variables, aux, aux2, and aux3. And this is the code. First, we are using an AND operation between A and B and C. And this operation, well, the result of this operation is going to be almacenated in the aux variable and aux2 variable. Then we're going to operate an OR between aux and aux2. And the value of this operation will be almacenated in aux3. Finally, we are going to negate the value of aux3 to obtain the final result that will be watched in the next video. Now, finally, we have the fourth circuit. We saw that we have an OR gate, AND gate, NOT gate, OR gate, and NOT gate. So to obtain a 1 here, we have 3 possibilities because it's an OR gate, and we're going to analyze one by one. So the first one is to have a 1 here and a 1 here. To obtain a 1 from an AND gate is just one possibility to have 1 here and a 1 here. And to obtain a 1 here from a NOT gate, it's that we have a 0 in the input. Now we're going to analyze this part. So to obtain a 1 from a NOT gate, we need a 0 here, and to obtain a 0 from an OR gate, we just have one possibility, is that we obtain a 0 here and a 0 here. So this is the first combination, where the inputs are 0, 0, and 0. Now we're going to see another one. To obtain a 1 here, we will have a 1 here and a 0 here. So to obtain a 1 here, it's basically the same when we have a 1 here and a 1 here and a 0 here. This one will change because to have a 0 here, we need to have a 1 here. And to obtain a 1 here, we could have a 1 here and a 1 here. So this is the another combination. When we have a 1 here, 0, and 1, which corresponds to this one. But if we see, in that case, to obtain a 1 here, we'll change to have a 1 here and a 0 here. So if we had a 1, sorry, a 0 here and a 1 here. So if we have 0, 1, and 0, we'll obtain a 1 here, and it corresponds to this combination 0, 1, 0. We have 1, 2, and 3 combination, and finally for the next combination is necessary to return here. We saw that I have 1 here and 0 here, but if we put a 0 here and a 1 here, we will see that to obtain a 0 here, we will have a 1 here and a 0 here. Sorry, a 0 here and number 1 over here. To obtain a 0 here, we need to have a 1. And over here, we have a 1 and we need to 0. And to obtain a 0, we need 0 and 0. So this is the last combination. And the input we will have 1. Input B, we will have 0. And output C, we will have 0, which corresponds to this one. So these are the 4 possible combinations to obtain a 1 and throw on the lead. Now we're going to analyze the code. This is the code. So we are using the same structure as an exercise 3. We are using 3 ports as an input and 1 port for an output. And this is the architecture. We are using 4 auxiliary variables that are aux, aux2, aux3, and aux4. And these are my operations. The first one is to negate the 8 port with a NOT. And this result will be almacened in the aux variable. The next one is to generate an operation between aux and B, and almacenate this one in aux2. Then we are going to operate B or C and almacenate this value in aux3, and negate this value of aux3 and almacenate in aux4. And finally, we will operate an OR operation between aux2 and aux4 in the output, and this will basically our code. Now we are going to see the functionality of this code in the FPGA board.